10.5. Section 10.5 talks about the derivative from a numerical and graphical viewpoint. Okay? So in the previous section, you learned about the concept, the average rate of change, and in this section, we're going to learn about or connect that idea to a new concept called the derivative. The ideas presented in this section is mainly for intuition, okay? Mainly for intuition to connect the difference quotient to the concept of limit that we talked about and to form the definition of a derivative, and then talk about how to find it by using numerical and graphical viewpoints. Our ultimate goal is to get to the algebraic viewpoint, which is discussed in section 10.3. And after, not 10.3, we did that before, 10.6, right? 10.6 will be the algebraic viewpoint for the derivative, and then after that section, you'll get away from that and use the rules for differentiation. So it's a gradual introduction to what the derivative is, okay? So let's start with the definition. Assume that f of x is defined for all x in some open interval about x equals a. So assume that f of x is defined for all x in some open interval about x equals a. The instantaneous, let's use red, the instantaneous rate of change of f of x at x equals a is defined as f prime of a. This is not a 1, this is a prime. F prime of a equals the limit as h, I'll write that up a little bit higher, as the limit, it's written as the limit as h approaches 0 of f of a plus h minus f of a all over h. So we have that is the instantaneous rate of change, assuming that the limit exists. This quantity here, f prime of a, is called the derivative. It's called the derivative of f of x at x equals a. It's called the derivative of f of x at x equals a. So f prime of a is notation for derivative. It's also known as your instantaneous rate of change. So it connects the idea of a limit with the difference quotient that you learned. Putting it all together gives us the definition of the derivative of your function f of x at x equals a. So a couple of things to note. For f prime of a to exist, a must be an interior point of the domain of f. So in other words, it cannot be an endpoint of a closed interval. The limit must exist and it must be finite. Okay? When f prime of a exists, we say that f is differentiable at a. We say f is differentiable at a. So you'll have to get familiar with the terminology. So practice it as you're working through your homework and as you're speaking and answering questions in class. If f is not differentiable at a, or we say that it's not differentiable at a. Okay? So if the derivative exists, we say that the function is differentiable at a. Otherwise, we say that the function is not differentiable at a. Okay? Remember that the instantaneous rate of change of f of x at x equals a is defined by f prime of a equals the limit as h approaches 0 of your difference quotient. Okay? So h is approaching 0. So let's look at an example. Let's look at an example with several parts. Did you get that on the previous page? Okay. All right. So the air temperature one balmy summer evening at your summer resort near Maxwell Montes, T hours after 5 p.m. was given by the function f of t equals 880 plus 2t squared minus 20t degrees Fahrenheit, where t is greater than or equal to 0, but less than or equal to 4. What was the temperature at 8 p.m. and how fast was it dropping? How do we find that? How do we find the temperature at 8 p.m.? Let's break it into two parts. How do we find the temperature at 8 p.m.? Go ahead. Talk a little bit louder. Good. You plug 3 in for T. Very good. So first you interpret 8 p.m. That corresponds, very good by the way, that corresponds to T equals 3 because it's 3 hours after 5 p.m. So we have F of 3 is equal to 880 plus 2 times the quantity 3 squared minus 20 times 3. And when you evaluate that, you get 880 plus 18 minus 60. So that will give us 838 degrees Fahrenheit. That would be your temperature at 8 p.m. That's the temperature at 8 p.m. Okay? Now, what questions do you have about that? None? Okay. So now we want to figure out how fast was it dropping? How fast was the temperature dropping? So below I've given you a couple of tables for the average rate of change, of F over the closed interval 3 to 3 plus H. Do you want to practice just writing out the average rate of change for practice? Okay, so let's do that. So your average rate of change, remember, is F of 3 plus H minus F of 3. What are we finding again? What are we writing out right now? What is this? What are we writing out? We're writing the average rate of change. Online we're saying the average rate of change, and in class we're saying the difference quotient. It looks like the difference quotient, right? But remember, we're finding the average rate of change over this interval, and because it's over the interval 3 to 3 plus H, it looks just like the difference quotient. Does that make sense? Okay, cool. So, good. That's equal to 880 plus 2 times the quantity 3 plus H squared minus 20 times the quantity 3 plus H. And then we're going to subtract, what's F of 3? What's F of 3? So 838, good. So we subtract 838, divide it all by H. So that is the formula for your average rate of change, okay? That's the formula for the average rate of change. Now, here are the tables for the average rate of change of your function f over this closed interval 3 to 3 plus H. So here we have H. Notice that in order for us to figure out how fast it was dropping, we're being asked to figure out what was the average, not the average, we're asked to figure out the instantaneous rate of change. Does that make sense? So whenever you look at the values here, notice that the values are getting closer and closer to 0 because that's what we're evaluating or finding here. Okay, so notice that as H gets closer and closer to 0 on either side, what are the values getting closer and closer to? -8, very good. So this means This implies or this means that f prime of 3 is equal to -8. So that means that the temperature was dropping at a rate of 8 degrees Fahrenheit per hour. Okay? Questions? So the question online was, can we go back through that? And because I didn't quite understand how we could grab this information from these tables, okay? So remember that the derivative, so an aside, remember that f prime of a is equal to the limit as h approaches 0 of f of, in this case, we're finding f prime of 3. So we can write that. So that's equal to f of, the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. Now, notice that h is approaching 0 here. So the way we've talked about that is in section 10.1, we talked about the numerical, estimating a limit numerically. So whenever we're discussing that, my filter's falling out. Whenever we're discussing that, we have to choose values of h close to 0. They're getting closer and closer to 0 from the right-hand side and from the left-hand side. Do you remember the left and right-hand limits? Okay, so this is approaching 0 from the right. This is approaching 0 from the left. So if you observe your output or your average rate of change values, that means you take these values, substitute them in here. Your output would be -6. Your output would be here, would be that. And then you get your output here. They're getting closer and closer to -8. So that's how you get that. Yes, there's another question.
So are we not going to simplify that? Like, why do we do that?
You're welcome. Thank you, you're welcome. And then, so the question was, are you not going to simplify this?
Yeah, because we just found out that the rate of change after is -8. So
Right.
what is that?
This is your average rate of change.
Okay,
This-
so I plug anything back into that once you find that?
This is your average rate. Oh, what did I just press? That's your average rate of change. The purpose of finding that was for you to see or make the connection that for this table, you are taking these values, 1, substituting it in for h here, and that's how you get -6. You substitute in 0.01 here for h, you're going to get -7.98, and so on. So it was to make that connection with the information coming from the tables. What other questions do you have? Okay, so then the last connection that you need to make then was using the average rate of change. Remember that whenever you're asked to find how fast it was dropping, you're asked to find the instantaneous rate of change. So you're asked to find the derivative of your function at 3. So that's how you find this is equal to -8. That's the limit as h approaches 0 of your average rate of change. Okay, got it? No response. Do you have it?
Yes.
All right. So, all right, good. So now let's talk about secant and tangent lines. I put here we're going to watch a video, but we're not going to watch a video. Okay? Secant and tangent lines. So secant is derived from the Latin word secans, which means cutting. So just to show you graphically what's happening, you have a graph, you have a function like so. It doesn't have to look like that, just a function. Then you have a couple of points here and here. I can do the graph better. That's not so good. Let's make it a little bit better. So you have a point here, you have a point here. You draw a line through the points. You have, that's your secant line. The tangent line then, if you want the tangent line at this particular point, it takes this line. It's like you have two separate pieces. And you're taking, or you have two fingers here, one and here and one here, and you're taking it and you're pinching them together until you get here. So as you pull this point to this point, pulling this point to this point, I'm not going to use a different color, pulling this point to that point gives you this line. That line is called the tangent line. Okay? So the secant line moves the 2 points, it pinches them together and forms this line. Okay? So, definition, the slope of the secant line through the points on the graph of f where x equals a and x equals a plus h is given by f of a plus h minus f of a all over h. So it's given by your difference quotient. The slope of the tangent line through the point on the graph of on the graph of f where x equals a is given by m sub tan for the tangent line. That's given by your derivative, f prime of a. So in other words, it's the limit as h approaches 0, pressing random points, of f of a plus h minus f of a divided by h. Okay, so the slope of the secant line is just your difference quotient. The slope of the tangent line is your derivative. Okay? So now what we're going to do is go through some examples. Okay? This is not typically how you would find the derivative. This section, remember, is the intuition behind that. Okay? So using the concepts that we've learned so far, we're going to calculate an approximate value of the derivative of f at -3 if f of x is equal to x over 3 minus 1. So that's equal to, so we'll say here f prime of -3 is equal to, or approximately, let's say that, so this is equal to the limit as h approaches 0 of negative, or why do I keep pressing that? F of -3 plus h minus f of -3 all over h. So what I'm going to do, I'm going to choose a value of h really, really close to 0. Okay, because that's what we're doing here, right? Are you with me? Okay, so I'm going to say this would be, since we're calculating an approximate value, this is going to be approximately. Wavy equals means approximately. That's approximately f of -3 plus 0.0001, just choosing a value close to 0, minus f of -3 all over 0.0001. that, when you substitute it in, so you'll be taking this value, substituting it in for x here. When you do that, you're going to get that that's equal to 0.3333 repeated. So in other words, that's going to be 1/3, which will be your final answer. There is a better way that we can do that, and we'll learn that way in section 10.6. Right now, we're just giving an approximation. Okay? So now in part B, we have to find the equation of the tangent line at the point on the graph where x is equal to -3. So, since we're finding the equation of the tangent line at the point on the graph where x is equal to -3, we first have to find f of -3, right? Because we need to find our y value. Are you with me? So we need to find our y value. So f of -3 is equal to -3 over 3 minus 1. That's equal to -1 minus 1, which is what? -2. Good. So that means that the point that we're really considering right now is -3 comma -2. That's the point we're looking at. Okay? So we have, using our point slope formula, this is y minus -2 is equal to your slope. What is your slope? 1/3. Very good. It's 1/3. Remember, your slope of the tangent line is your derivative. Good. So that's equal to 1/3 times the quantity x minus a -3. So that means y plus 2 is equal to 1/3 times the quantity x plus 3. And then we can put this in slope-intercept form. So that will give us that y plus 2 is equal to 1/3 x plus what? 1. Good. Or we get y is equal to, we subtract 2 from both sides, and we get y is equal to 1/3 x. What's the rest? What's the rest? Minus 1. Good. And that's your equation. That's your equation. What questions do you have? Okay. All right, let's look at another example. Same idea, different function, different point. Calculate an approximate value of f prime of -1 if f of x is equal to 1 minus x squared. So again, remember the concept that the derivative means you're taking a value, in this section you're just taking a value close to 0 on either side, and then you're using -1 as your a. Okay? So I'll just tell you to let h be equal to 0.0001. Take a couple of minutes and do parts A and B. So we said take h to be equal to 0.0001. So that means that we have what? F of, what's your setup? F of what? Plus h, which is 0.0001. Good. Minus f of what? Good. All over 0.0001. So f of -1, what did you get for f of -1? 0. Good. So that will give us f of -0.995 0.099 minus 0 over 0.0001. And whenever you evaluated that all, you get that's about 1.9999, which means you get that it's about what? What number? 2. 2. Good. So it's about 2. Okay? Now, to find the equation of the tangent line at the point on the graph where x is equal to -1, you have to find the y value. We did. F of -1 was 0. So the point that we're considering here is what? What's the point? The y, the x, y. What's the coordinate? Talk loud. -1, 0. Good. So using point slope formula, you have y minus 0 equals 2 times x minus -1. So that gives you y is equal to 2x plus 2. And that's it. Okay? Notation for derivatives. It's important for you to understand this. You have prime notation, which is what we've been using. You have f prime of x. The other notation is called Leibniz notation. So df over dx means the derivative of f with respect to x. df over dx means what? I just said it. It means what? This is to see if you're listening. I just said this is Leibniz notation and I told you what it meant. What is df over dx? I can't hear you. Go ahead, online. No, they said the derivative of f of x. How do you read this? No, it's not the derivative of f over the derivative of x. It's the derivative of f with respect to x. This is the derivative of f with respect to x. That's how you read this, the derivative of f with respect to x. You can also be given a function as y, so you can find y prime. That's the derivative of y. Or you can use Leibniz notation to find the derivative of y. How do you read this? Yes? Good, the derivative of y with respect to x. If you want to evaluate your derivative at a point, then we've been writing f prime of a certain value, but you can also use Leibniz notation and you can write the derivative of f with respect to x and write this bar and write x equals 2 at the bottom. This means the exact same thing as this. That means evaluate your derivative at that specific value. Got it? All right. Next example. Next example. We want to estimate the indicated derivative given the function s equals 4t plus t squared. So we want to estimate the derivative of s with respect to t at t equals 2. Okay? So here we're estimating this value. So what we do here is we have to find s of 2 at some point. But what we're doing is we're estimating s of 2 plus h minus s of 2 over h. We're really finding the limit as h approaches 0 of that, right? But as we've been doing, we're going to say h is equal to 0.0001 because we're doing an estimation. So that's going to be approximately. Since we have to find s of 2, let's find s of 2. S of 2 would be equal to what? Talk it through and tell me. 4 times what? 2 plus what? 4, because that's 2 squared. So you get 8 plus 4, which is 12. Good. So you would have S of 2 plus H. So because H is 0.0001, this would be 2.0001. So this would be 4 times 2.0001 plus 2.0001 quantity squared minus 12, right? So all of this here is S of 2 plus H. We substituted that in there. Minus S of 2 all over 0.0001. You enter that into your calculators, you're going to get that's equal to 0.00080001 divided by 0.0001. Once you evaluate that, you're going to get 8.000100000001. That number is really close to what? 8. So that's why we say this will be 8. All of that to say that the derivative of S evaluated at t equals 2 will be 8. And in the next section, you'll learn a nicer way of doing this. What questions do you have? Okay, so let's talk about the average and instantaneous velocity. Let's talk about the average and instantaneous velocity. So for an object moving in a straight line with position S of t at time t, the average velocity from time t to time t plus h is the average rate of change of position with respect to time. So the average velocity is equal to S of t plus h minus S of t all over h. The instantaneous velocity at time t is v equals the limit as h approaches 0 of S of t plus h minus S of t all over h. So in other words, it's just the derivative, right? It's just equal to the derivative of S with respect to t. So in other words, instantaneous velocity is the derivative of your position with respect to time. Okay? So we've talked about rate of change, average rate of change, and then we've connected that to instantaneous rate of change. Now we have average velocity and instantaneous velocity. Okay? So it's the same, you approach the problems in the same way with the examples we've been talking about throughout this section. Okay? So all of this leads us to the formula for the derivative. It leads us to the formula for the derivative. That is given by, the formula for derivative is given by f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Okay? So you'll need to make sure you know this. This is the formula for the derivative. So a few observations. with what happens to the graph of a given function whenever you're talking about the derivative. Okay? So, given the graph of a function f, we can get a rough sketch of the graph of its derivative by estimating the slope of the tangent to the graph of f at several points. So here, I've sketched the graph of a function, y equals f of x. Notice that this function is decreasing when x is less than 1. When x is less than 1, your function is decreasing. When x is greater than 1, the function is increasing, right? So whenever we want to talk about the derivative of this function here, notice that again, the function is decreasing, which means your slope is what? Positive or negative? Negative, good. So whenever you're talking about the derivative, remember that's your slope of your function, right? So that means that your derivative is negative for x less than 1, which means your function looks like this. It's negative here, okay? Because it's below the x-axis, so it's negative, okay? When f is increasing, whenever x is greater than 1, the slopes are what? Positive. So f prime is positive for x greater than 1. So notice that it's positive here. So it goes above the x-axis. Okay? So you can provide rough sketches of given functions. Okay? Or provide rough sketches of the derivative for given functions. Okay? So that's the derivative with the numerical and graphical viewpoint. That's the derivative of a function with the numerical and graphical viewpoint. Now let's move on to section 10.6, which is the derivative from the algebraic viewpoint.